So let's get a rocking and a rolling here. So I'm going to be looking at, to start, section 1.1. And again, the book pages that I'm kind of referencing are the book pages that I put in the content library you could view from the online book through My Notre Dame. Domenico, what's up? So if you go to My Notre Dame and you go to the links there on the class bulletin board, they'll have like a first hour trig link. And then that'll prompt you open up Teams. And if you open up your class notebook through Teams, it'll pop in. I can help you at the end of the hour with that if you're still having trouble. Okay. So this first chapter that we're going to look at is going to be a review of some concepts from our Algebra 2 course last year. So we're just going to start by talking a little bit about what a function is and some different representations of functions and examples of things that are functions or not and ways to kind of figure that out. So we'll just start with our basic definition. So we'll say that a function from a set D to a set R is a rule such that every member of D pairs with exactly one member of R. So this set D we call the domain, and this set R we refer to as the range. And hopefully this sounds familiar. This was kind of where we started last year in your Algebra 2 class. Would have been just kind of the general description of what a function is. But it's been a year, so we'll go through it again. So one way we can represent a function, or even the more general is a relation. One way we can represent those things is with something called a mapping diagram. So in a mapping diagram, we usually draw two circles, one for the domain and one for the range. And then we'll put like a dot to represent some values in the domain and a dot to represent some values in the range. I'm just going to call them kind of generically x1, x2, x3, and y1, y2, y3. And then we just kind of draw an arrow to show how they're paired together. So maybe this is our pairing. So let's use the definition of a function here to look at what we've drawn to decide if this is what I've drawn is a function or not. So it says in the definition that every member of D pairs with exactly one member of R. So the first thing I'm going to do is I'm going to look at my members of D and make sure that they're all paired with something, which they are. Next, I'm going to go over and look at my members of R and make sure that they're Nope, that's all I need to check. I just need to make sure that each member of X is going someplace and that it's going only one place. Okay with that? So I only have to look at the domain. I have to make sure that every member is going someplace and that it's going only one place. What's happening at R does not matter. So let's look at another one. So again, we'll just draw our generic domain and our generic range here. And let's say that, oops, I thought I changed colors. Let's say that we have this. Is this a function? No. What's the problem? Yeah, not all the domains are being used. Perfect. Now, what if we added in this? Is this a function now? Yes. Does it matter that one of the y's is being used twice? No. Does it matter that one of the y's isn't being used at all? No. Because a function, really all that we care about is the x's. Everybody's cool? Okay. Let's look at one more example and then we'll kind of move forward. Again, this was stuff that we should have hit pretty hard last year, and it's the second time around, tends not to be too difficult. So again, we'll just draw the same kind of drawing. And let's say that we have this one. Is this a function? No. What's the problem? Yeah, x1 is going to two different places. If instead we had done this, is that a function now? Yes. Okay. Very good. Another way that we can represent a function is with a graph. So maybe we could ask a question like, does y equals x squared plus 2 define y as a function of x? Now don't let the wording here throw you. When we say y as a function of x, it just means that x would be your independent variable and y would be your dependent variable, just like every other time in our Algebra 2 class is exactly how we treat x and y, right? You pick x's to find y's. So that's what we're saying here. Now, ideally, you could look at the equation and have a pretty decent idea of what this graph looks like based on what we did in Algebra 2 last year. Can anybody do that still? Tyler?
Well, that follows the y equals mx plus b formula, so it's a straight
line. Well, it's x squared, though, right? It's not 2x, it's x squared. So it's not a straight line, but I like where your head's at. Let's look for something familiar, because the form here should be something that we could possibly recognize. If you don't, it's okay. It's been a year. Anybody else want to take a stab? Landon?
What do you say? Like we simplify that to x plus
You don't even need to try to factor it. This one doesn't factor, as a matter of fact. So the trick here is just recognizing that this thing is quadratic, right? Because it's got an x squared as the biggest degree x in it. And what do all quadratics look like? The graph? They're parabolas, right? It's just like a U shape. Everybody kind of remember that from last year? And we can tell whether the U shape is going to open up or down based on the sign on the leading coefficient. In this case, the sign in front of the x squared is positive. Since there's nothing there, we understand it to be a 1x squared. So we know the parabola is going to open up. And because it's just got the +2 at the end, we know it's just going to be like translated up 2 units, but that part doesn't really matter because any parabola that's opening up would be good enough for us to determine whether the thing is a function or not. If we look at this graph, is this a function? Do you guys remember from last year? Yeah. What did we use to check that? Yes, Jane? Perfect, yes. So the easiest way to check to see if a graph does represent a function is with a vertical line test. Very good. So the way we do that is we're looking for, is it possible to draw any vertical line that intersects the graph in more than one place? So vertical lines are straight up and down. So if I draw that vertical line, it only intersected the graph one place. If I draw this vertical line, it only intersects the graph one place. No matter where I draw that vertical line, it's only going to hit the graph one time. So we know that this thing is a function. If there's any place where the vertical line intersects more than once, it's not. So for example, let's say we have a graph that looks like this. Does that represent a function? No. Why not? Yeah, I can draw a vertical line that can intersect the graph more than one time, right? This is intersecting it in 3 places. Does it matter that if I drew my vertical line here, it can intersect it only one time? No. All I need is one vertical line that intersects it more than once. It doesn't matter how many vertical lines intersect it more than once. It just needed to happen one time. Is that okay? Okay. And then the third most common representation we have for a function is just function notation. So let's just write a definition here for that, since there's no need to write a definition for a graph. And checking if it's a function or not with a graph is pretty easy. So function notation, the way we write it is that y equals f of x is the way we write a function notation. So the way we interpret this is that we say that y is equal to the value of f when x, or at x, maybe I should say. It's probably the clearest way to do that. So again, the way we do this is it states very clearly which ones are independent and dependent variables. So when we use a function notation, since it's quite clear doing that x is what you're plugging in, which makes it the independent variable, and y is the value you're obtaining from x, which makes it the dependent variable. That's why we use this notation frequently, as it eliminates the guesswork of whether y is the independent or dependent variable. So, for example, if I say that f of x is equal to 3x minus 4, and I want to find out what f of 2 is, all that's telling me to do is plug 2 in for x and evaluate. So this kind of implies to us then 2, 2, the coordinate 2, 2 is a point on, well, we'll write it as, be very specific, is a point on the function f of x equals 3x minus 4. Everybody kind of remember doing that with the function notations? It's likely you did that even in your Algebra 1 course from way back when. But it's important, again, that we refresh on these notations. Like, one of the things that makes math difficult for some students is we have a lot of different notations and a lot of different representations and a lot of vocabulary. And if we're unclear about something, it's hard to understand the next concept if it's written with a bunch of notation vocabulary that you're still uncertain about, right? So again, if I'm doing anything that we're unclear about, or I'm using any vocabulary, any symbols you're not sure about, feel free to speak up. It's very difficult to understand something like the big idea if you don't understand like the little pieces that are making up that big idea, right? Well, that was the first section, so we're doing good. Hi, you are here. So we have these 2 seats are open. You're welcome for either one of them. I know how you love the front row. That was a joke. I don't think I've ever seen you sit in the front row. Okay. So if you remember from our definition of a function, the set of x's is our domain, and the set of y's is our range, right? The inputs are our x's. Those are the things in our domain. That's our startings. And what they're paired with, the outputs, or the y coordinates, those are our range. So there's a couple of different ways that we can describe a domain and range. One of them is called interval notation, which we used a little bit in our Algebra 2 class. So an interval notation is just a way of representing a set Not all sets can be represented with interval notation, but if you have a continuous set, those are ones that interval notation is useful to use. So for example, let's say our set of numbers is all of the x's that are greater than 5. So that would include things like 6, 7, 8, 9, but it would also include things like 5.1, 5.01, 5.0001. So there's infinite number of numbers in this set, right? We wouldn't want to try to write those all down. So what we're going to do is come up with a compact way of representing that information. So when we write an interval notation, the format is we write the lower bound first, and the upper bound will be second, separated by a comma. And then we'll use a parenthesis or a bracket. So a bracket is if it's like a less than or equal to or greater than or equal to. And a parenthesis we'll use for just less thans or greater thans. And the same thing at the other end. So again, a parenthesis or bracket to end our interval notation. So if I'm looking at the set of x's that are greater than 5, what's the lower bound to that set? 5. That's the smallest number that's going to bound that everything in that set is either equal to or bigger than that number. In this case, it's only bigger. Okay. What's the upper bound for this set? Infinity, right? Because the numbers that are greater than 5 go on forever. You can always pick another number that's bigger. So is 5 included in the numbers that are greater than 5? No, right? So this is, again, because it's a strict inequality, that's the same way of thinking about it. We should use a parenthesis. Is infinity a number we can actually reach? No, it's kind of more like a concept, right? You can't like plug infinity in and do calculations with it. So that'll also get a parenthesis. Infinities always are going to have a parenthesis stuck on them. So that's easy to deal with there. Whenever you write an infinity, you know that it's going to get a parenthesis with it. Do you guys remember doing this a little bit from last year? We did it a lot, potentially. Let's do another one. Oh, and just FYI, if you really want to be very precise about this, since the variable here was an x, the way you'd write this set is you'd say x is a member of that interval from 5 to positive infinity. So that symbol there is like a curvy, like a curved E. You know, like the letter E usually has points at the end. This is just like a C with an extra, you know, that makes it look like an E. You guys get that? It's okay? That's what that symbol means. Just it's a member of that set. Sorry, I almost forgot that part. We start being a little pickier about that, how well you're doing your notations as these classes get, you know, as you get deeper into your math classes. This was not something I cared about in the Algebra 2 class the first time you're seeing interval notations. It is something we'll care a little bit more about in this class as it's, you know, the second time. So we're going to be a little bit more specific with our notations. Okay. Let's say we have this set of numbers where -5 is less than y, which is less than or equal to 10. So again, I would start with the lower bound here, which in this case would be -5. Yeah, that's the smallest number that everything is, you know, that everything else is either above or equal to. So again, the things that are between -4 and smaller than positive 10, you know, so you'd have like -4, -5, -6, 0, 9, 8.3, 0.0008, you know, all that stuff. What's the upper bound? 10. Now, if I look at the inequality involving the 5, that's a strict less than inequality, so I should get a parenthesis on the 5. Again, 5 is not a member of that because 5 is not less than 5. Or, I'm sorry, -5 is not less than -5. And then the 10, the inequality involving the 10 is a less than or equal to. So at the 10, we're going to use the bracket. And then just like before, because the variable here is a y, we're going to say y is a member of that interval. Okay. One more example of intervals before we move on. So this one's a little bit different because this is an OR inequality, right? So on an OR inequality like this, you're going to need to have two intervals. So you'll write one interval for the first inequality and one interval for the second one. And then I'll show you the symbol we used to join them together if you don't remember. So we'll just look at them one at a time. Everybody good with that plan? All right. So if I look first at a is less than -2, the things that are less than -2 would be like -3, -4, -5, all the way down, right? Everybody's good there? So what's the lower bound on that inequality? -infinity, right? Because you can keep picking another number that's smaller. And the upper bound then is, we're just looking at the first inequality, -2. Everybody's okay with that? That if you're talking and listing all the numbers, that are less than -2, the last number, -2 is bigger than everything else, or equal to. Big, just strictly bigger in this case. Lily?
I just want to make sure it's -infinity because a is less than 2, right?
Right.
Okay.
Yeah, if it was a is greater than -2, it would be -2 would be the lower bound, and positive infinity would be the upper bound.
Okay.
Right? So because greater than -2, you'd have like -1, 0, 1, 2, 3, 4. We're counting up to positive infinity. Less than -2, the numbers we're interested in be like -3, -4, -5. We're counting down to -infinity.
Okay.
Does that make sense?
Yeah.
So again, if you just kind of, okay, what numbers are involved? Am I counting up or am I counting down? You should be able to determine whether it should be a positive or negative infinity. That's kind of the easiest way to think about it, is just to like, okay, what is this symbols really saying? You know what I mean? Okay. So the infinity, we know, always has a parenthesis. And the -2 has a less than with it, so it should get a parenthesis. Now, what we do with the OR is we're going to use the union symbol, which is like a U without a tail on it. Is the mathematics symbol we use there. That symbol is the same thing as OR. In set language, it's called the union. That's not important that you know the name for it, just rather how to use it. But it helps me remember which symbol is which, because the U in union looks like the symbol. Then we'll look at the other inequality. So a is greater than or equal to 5. So the numbers we're talking about there are like 5, 6, 7, 8, 9, 10, etc. The lower bound is 5, because we're counting up from 5. And the upper bound is positive infinity. Very good. So on the positive infinity, I always put the positive sign on there, mostly for me. It's not wrong if you left that off. It would be wrong if you left off the negative sign on the negative infinity, but you don't need to write the positive one on the positive infinity. I always do it for clarity's sake. But, okay. So the infinities, again, always get a parenthesis, so I'll just put that in right there. The inequality attached to the 5 is greater than or equal to, so the symbol I need to use at the 5 is the bracket. And again, we would say A is a member of that set. So far, so good. Hopefully we remember doing these things, right? In our Algebra 2 class, that it's not a complete start from zero. What I want to talk about next is a new topic, or newish topic. It's not something we talked about directly in our Algebra 2 class, but there were things that we did in our Algebra 2 class that are like, this is building from. Okay? So what I want to talk about is implied domain versus relevant domain. So in our Algebra 2 class, when we were looking at the domains or ranges for functions, we were always looking at the relevant domain. This is what we found last year in our Algebra 2 class. The implied domain is like something that would be based on the context of the question. So in a symbolic question where we're just saying, what is the domain of f of x equals x? Like the implied domain there would be all real numbers. If it was, the function f of x equals x represents the number of people needed to screw in a light bulb, or x number of light bulbs, then the implied domain there would be like the natural numbers, the positive whole numbers, because you can't have half of a person or half of a light bulb, right? You can't have a negative person or a negative light bulb. Like, those things don't make sense based on the context of that question. That's what we mean by implied. But almost always we're just going to be interested in the relevant. The relevant domain is always a subset of the implied domain, or equal to. It could be the same size, but it's always going to be, it cannot be bigger than the implied domain. So it's basically like when we're trying to figure out a domain, we start with the implied domain and then we narrow it down based on the actual function that we're looking at. All right. So let's look at a couple of examples here. So let's look at this function first. So f of x equals 2 times the square root of x minus 4. So because we're given no other information in this problem, there's no context to this, we can assume the implied domain would be all real numbers. Everybody's okay with that? However, there is a function or a operation going on in this function that we know can cause some problems. Does anybody recognize the operation in there that can cause some problems if we're not a little bit careful? The square root, right? Can we square root any number we want? No. What numbers give us a problem? negatives, right? We can only square root numbers that are greater than or equal to 0, right? The square root of 0 is 0. Anything positive we can handle, but the negatives, no bueno, right? So my relevant domain is going to have to account for the values of x that give me a negative symbol underneath the square root. Everybody agree with that? That I don't want those ones. So the easiest way to do this is you just take the stuff that's under the square root and you say it has to be positive. I should say non-negative. Is everybody okay with that? And then if I just solve this inequality for x, I can add 4 to both sides. And I know that my relevant domain should be x is greater than or equal to 4. Now I would want you to write this in interval notation. In this course, I would not accept for full credit just the inequality, and the directions would stipulate to like give the domains in interval notation or whatever. So here, the lower bound would be 4. The upper bound would be positive infinity. And because the symbol attached to the 4 is a greater than or equal to, that's a bracket. And the infinities always get a parenthesis. And since the variable is an x, we should write x is a member of that set. So of these like relevant domain questions, there's 2 operations that we're going to be frequently taking advantage of. One of them is the square root, because we know we can't square root negatives, so that'll be a frequently used one. The other operation that can give us problems is represented in this example. What operation in g of x can give us some problems? So what operations do we see? I see multiplication, right? 3 times x. I see addition, I see x plus 4. And I also see division, because I have a fraction there, right? And fractions and division are the same. Which one of those 3 can give us a problem? Division. Why?
You can't divide by 0.
Can't divide by 0. So that's exactly what I'm going to be worried about. So again, the easiest way to do this is to take our denominator and say that that cannot equal 0. Everybody's good with that idea? Worth taking a moment here and saying the implied domain, again, is all real numbers, since there's no context to this question, but often that's not going to be of particular import to us. And so if I solve for x, I subtract 2 from both sides, and I get x is not equal to negative 2. But maybe it's not entirely clear like how to get that into an interval notation, since it's not an inequality, right? Here's the trick to write this as an inequality. Is you're going to break it into 2 inequalities. You can either have x could be less than negative 2, or x could be greater than negative 2. And that'll include all the x's that are not negative 2. So that's the trick if you have a not equal to, is you can just break it into 2 inequalities, everything less than whatever it is, and then everything greater than whatever it is. And maybe that's not always entirely obvious, that trick, but like once you've seen it, it's pretty easy to employ. Yes, of course, yeah. So now we'll write this as an interval, or as interval notation, right? So x is less than negative 2. The lower bound there is negative infinity. Very good. The upper bound is? Okay. The infinity always gets a parenthesis, and the negative 2 should get a parenthesis. Very good. For the or, the symbol we use is that U with no tail. And then for x is greater than negative 2, the lower bound is negative 2. Very good. And the upper bound is positive infinity. The infinities always get a parenthesis, and the negative 2 should get a parenthesis. And then we write this, again, x is a member of. So if you look at that symbolically, it's basically saying, okay, from negative infinity to negative 2, and then from negative 2 to positive infinity, which, if you read along the number line, is the order that you encounter those things, right? If you're moving from left to right across a number line. Okay. We'll do one more example. Okay. This function says v of s is equal to s cubed, but we're given a little bit of context here, right? I tell you that v of s is the volume of a cube with edge length s. So here, the implied domain is not all real numbers, right? What kind of things couldn't be, what kind of numbers can't we use for an edge length? Negatives, right? So, and then you could debate whether zero length is still a measurement or not. I would say it is, but certainly you can't have a negative edge length. So the implied domain here is the real numbers that are greater than or equal to 0. Is everybody okay with that? Now, let's look at the function involved. What operations are involved with our function? Just cubing, right? Can that get us into trouble? It's not division, and it's not square roots, so it can't get us into any kind of trouble. So our implied domain and our relevant domain are the same in this case. Everybody's okay with that? So the only time the relevant domain is going to be smaller, at least for this class, is if there's involving the operations of square root or division. We've also seen logarithms or something, but I don't think we have an example of any logarithms in it because it's one of those things that I know that we need to review from last year. So I don't think I have any examples with logs until we've actually doing the log problems in the second semester. So I just need to convert this into an interval. So the lower bound here is 0. The upper bound is positive infinity. The infinities always get a parenthesis. And because it's greater than or equal to 0, the 0 is going to get a bracket. And then we just have s as a member of that. Okay. Do we feel okay doing these domains? Again, we did this a lot in Algebra 2. We were often concerned with domains and ranges, right? So it's not, shouldn't be wholly unfamiliar. now that I introduced a new concept with this implied domain, relevant domain piece, but it really didn't change what I was asking you to do for the most part. We're just making sure there wasn't some additional context that's like, okay, this is already saying that we can't have negatives or something because we're talking about a real world scenario or something. So we're interested in finding ranges, domains. Let's label these examples here as okay. So we're going to we found the domains. Guess I could have done a better job with that. And we're going to do now is find some ranges. So I'm going to use the same functions that we just looked at. And I'm going to include, when I wrote down the domains, because those things could be of particular interest to us. So the first thing that I'm going to take advantage, and I guess I should say this before we get going, finding the ranges algebraically is going to be almost always more difficult than finding the domains. But I'm going to try to show you guys give you guys some tips of how to make it a little bit easier. And these tips are going to take advantage of things that I remember from my Algebra 2 class. So we're going to take advantage of things that we remember from last year. And if you don't remember it when I'm talking about it, I'm going to explain it enough that hopefully it jogs some of that back. So the first thing I want to decide is the function that I'm looking at, this f of x in this case. Is this function increasing always or decreasing always? If it is one or the other, that makes life much easier when finding the range. So if I remember back to my Algebra 2 class, the graph of a square root function would look like something like this, or maybe it would look something like this, right? But it was either one of those two shapes. Everybody's okay there? So that red shape is increasing because as I go to the right, the graph is going up. It's getting taller. The blue graph is decreasing because as I go to the right, it's getting smaller, right? It's heading down. Everybody's okay with that idea? Now, it was easy to tell a square root function whether it was going to be increasing or decreasing, whether I was going to have something that was kind of red-shaped or kind of blue-shaped, because all it depended on was the leading coefficient. So if the leading coefficient was positive, we get something like the red, and if the leading coefficient is negative, we get something like the blue. Everybody's okay with that? Again, this is just stuff that we could possibly have remembered from last year. Now, I don't know that it would have been obvious that this was going to be important stuff to have remembered in this context, but that's why we're doing the examples and talking through it. I'm hopefully going at a pace that feels pretty reasonable. You guys still good with the pace? I'm not bulldozing anybody here? Okay. Okay. So, if my function is increasing, So let me just write a little bit of a note here. For increasing with a domain of like A comma B, the range is going to be the same bracket as on the domain, and the same parentheses, and it's just going to be like f of A comma f of B. So all we're going to do is, in our case here, is just plug in the lower bound and upper bound into f of x, and those will give us the lower bound and upper bound for our range. That's pretty easy. If it was decreasing, then the upper bound for the domain is going to give us the lower bound for the range, and the lower bound for the domain is going to give us the upper bound for the range. It'll just kind of flip. And you'll notice that the bracket and parenthesis stayed with the value that was had the bracket or parenthesis from the domain, right? That f of A kept the bracket rather than the bracket being in the beginning. It stayed with the f of A, so now it's at the end. Or stayed with the A, really. You guys see that? Okay. So here, if we go back to our actual example now, I know that my range is going to be, this is increasing, since that leading coefficient is positive. So my range will just be f of 4, comma, f of positive infinity. And the bracket and parentheses should stay the same as they were. Now when I plug 4 in, I have 2 times the square root of 4 minus 4. And 4 minus 4 is 0. And the square root of 0 is 0. And 2 times 0 is 0. Everybody's okay there? If I did f of positive infinity, we'll do some kind of hand-wavy arithmetic here with the infinity in there, because if I take infinity and I subtract 4 from it, what do I have left? Still infinity, right? Infinity is so big that subtracting 4 doesn't matter. And if I have infinity, I take the square root of it. What am I going to have? Still infinity, right? Taking the square root makes the number a little bit smaller, but if the number is infinitely large, if it makes it just a little bit smaller, it's still going to be infinitely large. And if I do 2 times infinity, that's still going to be infinity. So my range here is just going to be 0 to positive infinity. Again, I wrote down a lot of stuff. Very likely you could, once you have the hang of these, you don't have to write down. In particular, the infinity calculation is kind of silly to write down, but I just wanted to, like, let's be silly, right? Like, there's no reason not to be really thorough, and we'll hand wave as we get more comfortable. Tyler?
So, would one of the things that would change the infinity be like multiplying it by 0?
Yes. So if infinity is multiplied by 0, that becomes 0. Or if you had infinity minus infinity, you could call that 0. But really anything else, infinity is just going to stay the same. Well, it could become negative if you had like -1 times infinity, right? Would make it negative. Or any negative times infinity. would make it negative. But like you can, the sign change and 0, those are the things that can really affect it. But like adding 5 or multiplying it by 10 or dividing it by 6 or whatever, like doesn't change it. Okay. Feel okay there on that one? These should get a little bit potentially easier as we go. The next one we had g of x is equal to, oh shoot, what was it? 3x over x plus 2. And our domain here was, negative infinity to negative 2 union negative 2 to positive infinity. So I'm going to be interested in the same thing. I'm going to be trying to determine whether these are increasing or decreasing. And to do that, I'm going to take advantage of what I know about rational functions that we talked about last year, because when I look at that, that's what I have. So I remember rational functions have a vertical and horizontal asymptote, right? So the vertical asymptote is going to be the value of the denominator set equal to 0. So in this case, that would be negative 2. Oops. Color that. So I don't know, something over here. And the horizontal asymptote depends on the form that we have, right? So here, where I have x's in both the numerator and denominator, and the x's are of the same degree, I have an x to the first in the numerator, and I have an x to the first in the denominator. The horizontal asymptote is going to be the leading coefficient of the numerator, that's 3, divided by the leading coefficient of the denominator, that's 1. So the horizontal asymptote would just be at 3. Now that's a lot to ask that you remembered. Definitely okay not to have. Okay. So there's my vertical and horizontal asymptote. And then the graph then looks like just two hyperbolas that are kind of kitty corner from each other, like this. And I know they're in that pair because the leading coefficients were both positive. If one of the leading coefficients was negative, it doesn't matter in the numerator or denominator. They would be flipped. So you'd have on top, you'd have like this corner and this corner if you had one of the leading coefficients negative. If they're both negative, it's the same as what we just drew. Which is good, because basically what this is telling me then is that this first part of our domain is decreasing. If I look at that graph, right, as I move left to right, we're going down. And the second part is increasing. So that's going to make it pretty easy then for me to find my domains and range, or find my ranges. Is everybody okay how just looking at the graph I was able to determine increasing and decreasing, just looking at the picture? Again, if you forgot how to get the picture for something like this, which is totally reasonable thing to have forgotten because it's kind of complicated and there's a lot of detail there and a lot of things to remember and it's been a year, you could type it in your calculator and look at the picture. Not an unreasonable thing to do to just determine like the increasing and decreasing parts. Okay, so since this is decreasing, I'm going to be worried about f of negative 2. So when I do that, I have 3 times negative 2 over negative 2 plus 2. Which gives me negative 6 over 0. And what does that mean? That means we're in trouble, right? So what that's saying there, I don't want to see this. What's going to be this way? You know what? Let's not worry about that. Yeah, okay. So this is basically saying this is like the 0 is undefined, right? So this is like because it's negative 6 over 0, that's like a negative infinity. When you get something that's undefined, it's going to kind of represent it an infinity, whether it's a positive infinity or negative infinity based on the sign. And if I do negative infinity, oops. I have this, right? Everybody's okay here? Now, if I do negative infinity plus 2, that doesn't really make any kind of difference, right? That's still going to be negative infinity. You guys buy that? But if I have 3 times negative infinity over negative infinity, that's a lie. We still have 15 minutes. If I have 3 times negative infinity over negative infinity, that's really just like 3, right? You guys buy that? So this first part I have is negative infinity to 3. Oh, boy. Yeah, okay. So I misspoke here a moment ago when I was figuring out this sign. Since I know that this is the lower bound, I know the infinity has to be negative. Not because of the sign of the negative 6, but because I know this is the lower bound for this part of the interval. I needed to clarify that because we're about to get another 0 over negative 6, but I'm going to call it positive infinity for a different, because it's the upper bound, and I want to make sure that everyone's going to be like, wait, what, this is not what you, and it's just, okay, I messed up. So it's the lower bound piece that's the issue. So now we'll do the same thing. So now I have my lower bound is negative infinity, and my upper bound is coming from negative 2. And these are going to give us the same values. But because this is an upper bound, I'm going to use a positive infinity there. I just want to point out to you, I didn't write down any of the work because it's identical to the work that we just did above. That's why I didn't write down any of the steps to get 3 and 0 over negative 6. You're okay with that? You could also say here that if you remembered from your Algebra 2 class, you might have just been able to tell what the range from this is just from the function you had and gone like, oh, okay, I know the domain is everything but the vertical asymptote and the range is everything but the horizontal asymptote for a simple rational function, which is what this was. But that's a lot more remembering, I think. But that would have been reasonable also if you were thinking like, hey, isn't it just like everything, like, isn't that? Yeah, it was. It is. And that might have been the easier way to do it, but it required a lot of remembering. And our last one, and this will be the last example for today, so we're going to stop at this point. You guys have done a very nice job paying attention and everything, and I really appreciate it. And your participation's been good, and everybody looks pretty engaged and trying hard. So good job. This is the last example for today, and then we'll stop because, oof, right? So this was our last example. We had this where the domain we said was 0 to positive infinity. Remember, this one had the added context that we were talking about the volume of a cube with side length or edge lengths of s. So again, I'm going to try to determine whether s cubed is increasing or decreasing. What do you guys think? Yeah, for sure, right? The whole way. Like if I take 1 and I cube it, okay, that stayed the same. But if I take 2 and I cube it, I get 8, that's bigger. 3 cubed 27, that's bigger. We're just getting bigger, right? Everybody agree with that? And you just kind of anecdotally think about it that way is okay. If you remembered back from your Algebra 2 class, the graph of like y equals x cubed would look like this. And the part that we are interested in, since our domain is just the positive reals, was here. So again, we can tell that that's increasing. So it's really pretty easy there. So we have v of 0, which is b0 cubed, which is 0. And v of positive infinity, where positive infinity cubed is just infinity. So our range is 0 to, catch up please, to positive infinity. And that one turned out to be the easiest one of the lot by quite a bit, right? It was the simplest function when you looked at it. It just had that implied domain thing that would have been easy to miss if you're just kind of going willy-nilly through it. But it turned out to be a pretty easy range to deal with. So your homework is going to be numbers 1 through 12. So again, in the content library, you'll see the chapter 1 problems are located there. So those are the problems. I would prefer when you're doing your homework that if you're you can write on this same sheet, but write like on a separate column. Don't try to like cram your work and answers right next to the problem. Like use some extra space. It's okay. Don't try to like write the answers in your work and cram it all right next to the problem. Like give yourself some space. Make it readable for me. Okay?